Hello everyone, I represent the Facultad de Ingeniería at the Universidad Autónoma de Yucatán and the Institut des Nanosciences de Paris at Sorbonne Université. Today I will present our work titled Thermally Tunable Corner and Edge Electromagnetic Modes in VO2 for Near-Field Radiative Heat Transfer. To understand the core of this research, we first need to consider the dual nanoscale regime. In this regime, both the membrane thickness and the vacuum gap fall well below the thermal photon wavelength. When this occurs, radiative transport is no longer carried by the flat surfaces, but concentrates at the geometric singularities of the membrane, namely its corner and edges. Prior work has shown that in silicon carbide or SiC membranes, these corner and edge modes can account for up to 81% of the total near-field radiative heat transfer. Extending this framework to materials with temperature tunable properties offers a completely new pathway to active control of near-field radiative heat transfer. This is exactly where vanadium dioxide or VO2 comes in. VO2 undergoes a reversible metal insulator transition near 68 degrees Celsius, accompanied by dramatic changes in its dielectric function across the infrared spectrum. Crucially, these changes imply that the real part of the dielectric function can become negative, allowing the material to support surface phonon polaritons. Our goal was to investigate how this transition affects the modes. To do this, we conduct a computational model analysis of corner and edge electromagnetic modes in 20 nanometer thick VO2 nanomembranes, and we perform finite element eigenvalue simulations, rising experimentally measure the electric functions for both the insulating and metallic phases. We then calculate the dispersion relation of the fundamental corner and edge modes and compare them with those in silicon carbide membranes of the exact same geometry. The results shown in the maps are quite revealing. We found that absolutely no corner modes exist for the insulating phase. This happens because in this phase, the real part of the dielectric function is never negative within the frequency range, meaning it simply cannot support surface phonon polaritons. However, corner effects begin to appear right at the transition phase and are fully preserved up into the metallic phase. Interestingly, the effects during the transition exhibit a stronger confinement, and this is clearly reflected in the dispersion relation, where the respective curves lie well away from the like line, demonstrating a redistribution of the Poynting vector at the membrane corners. So, in conclusion, our computational analysis demonstrates that the metal insulate transition in VO2 nanomembranes induce distinct phase-dependent shift. And the role of temperature as a control parameter enables the material to support surface phonon polaritons across its phases as temperature increases, providing a new mechanism for enable these corner modes. So this is all, and thank you so much for watching.